But what if we don't have 0 on the right side? What if we have some function stated there? Let's consider an example. Y double prime plus y equals 1 over cosinus cube x. We can write down same equation, y double prime plus y equals 0, and try to solve it, and after that we can use same trick as for first order differential equations when we solved it using Lagrange method. So we'll get lambda square plus 1 will be 0, will be characteristic equation, and when we solve it we will get lambda equals plus minus I. So we will get y1 will be cosinus x, y2 will be sinus x. Because real part here is 0, then we will get e power 0 will be 1, and here multiplier before I is 1, so will be cosinus x and sinus x. So general solution will be c1 cosinus x plus c2 sinus x. And now Lagrange trick. We presume that c1 and c2 are some functions. Functions c1 of x and c2 of x can be found from the system c1 prime of x, y1 of x, plus c2 prime of x, y2 of x equals 0, and c1 prime of x, y1 prime of x, plus c2 prime of x, y2 prime of x is f of x, where f of x is the function that is stated on the right side in the equation. So substituting here our functions, we will get c1 prime cosinus x plus c2 prime sinus x will be 0, minus c1 prime sinus x plus c2 prime cosinus x will be 1 over cosinus cube x. We can solve this system using Cramer's method. We will have cosinus x sinus x minus sinus x cosinus x. This matrix will be multiplied by c1 prime c2 prime, and answer will be 0, 1 over cosinus cube x. So determinant of this matrix delta will be determinant of cosinus x sinus x minus sinus x sinus x, which will give us cosinus square x plus sinus square x, multiply this and subtract one from other, which is trigonometrical 1. Delta 1 is when we substitute first column with the answer column. So will be 0 sinus x, 1 over cosinus cube x, cosinus x, which will give us minus sinus x over cosinus cube x, and delta 2 will be determinant cosinus x minus sinus x, 0, 1 over cosinus cube x, which will be 1 over cosinus square x. Now c1 prime will be delta 1 over delta will be minus sinus x over cosinus cube x, and c2 prime will be delta 2 over delta will be 1 over cosinus square x. So c1 will be integral of minus sinus x over cosinus cube x dx, which will give us integral d of cosinus x over cosinus cube x, and we will get minus 1 over 2 cosinus square x plus some constant a1. c2 will be integral 1 over cosinus square x dx, which is stable integral, which gives us tangent x plus a2. So general solution will be 1 over 2 cosinus square x plus a1 multiplied by cosinus x plus tangent x plus a2 multiplied by sinus x. One more method of solving such equations is Euler's method for equations with some special right part. So we have some equation plus p1y n minus 1 plus so on plus p and y equals some f of x. Solution of this equation is y taken from homogeneous plus y taken from non-homogeneous, and here we can find this yn using form of this function. So, right part and yn. If we have right part in the form Pn of x or some polynomial and k equals 0 is not the root of Pn of x, then this yn will be a0 plus a1x plus so on plus anx power n, and same as here, and these constants a0, a1 and so on we will have to find further in the problem. We'll denote this as p with wave of x, and if k equals 0 is root of Pn of x s times, then this yn will be Pn with wave of x multiplied by x power s. Same goes if we have Pn of x by e power alpha x. However, here we consider k equals alpha, not the root. Then we'll get same Pn with wave of x multiplied by e power alpha x. If k equals alpha is root s times, then we'll get Pn of x with wave by e power alpha x by x power s. One more case. If we have e power alpha x by Pn of x cosinus beta x plus qm of x sinus beta x, then we consider k equals alpha plus I beta if it's not the root, then yn will be e power alpha x pl with wave of x cosinus beta x plus ql with wave sinus beta x, and if k equals alpha plus I beta is root s times, then same as here will be multiplied by x power s. Now let's consider some examples. Let us have equation y triple prime minus 5y double prime plus 6y prime equals 6x squared plus 2x minus 5. Homogeneous version of this equation: y triple prime minus 5y double prime plus 6y prime equals 0. Then lambda cube minus 5 lambda squared plus 6 lambda will be 0. Then we'll have lambda 1 is 0, lambda 2 is 2, and lambda 3 will be 3. Then solution of homogeneous equation will be c1 plus c2 e power 2x plus c3 e power 3x. Now, how about non-homogeneous part? We have f of x that equals 6x squared plus 2x minus 5. And characteristic polynomial has one solution, lambda equals 0. So our non-homogeneous solution will take form x power 1 because we have only one solution, lambda power 0, by ax squared plus bx plus c. Same power as here, polynomial same power as here, but with unknown coefficients. If we open brackets, we'll get ax cubed plus bx squared plus cx. If this thing will be a solution of our initial equation, then if we substitute this formula into this equation, we'll get the equation that will hold true. Something trivial. But to do this, we have to first find y prime, which will be 3ax squared plus 2bx plus c. Y double prime will be yn double prime 6ax plus 2b, and y triple prime n will be 6a. Substituting this into our initial equation will give us 6a minus 5 6ax plus 2b plus 6 3ax squared plus 2bx plus c equals 6x squared plus 2x minus 5. If we expand these brackets, we'll get 18ax squared plus 12b minus 30ax plus 6a minus 10b plus 6c equals 6x squared plus 2x minus 5. Now, if we have 6x squared here, we should have 6x squared here, so 18a equals 6. 2x here, we should have 2x here. 12b minus 30a equals 2. And the rest will be minus 5. 6a minus 10b plus 6c will be minus 5. So a will be 1 over 3, b will be 1, c will be 1 over 2. And our general solution will be homogeneous part c1 plus c2 e power 2x plus c3 e power 3x plus non-homogeneous part 1 over 3x cubed plus x squared plus 1 over 2x. This will be our solution. One more example. If we have y triple prime plus y double prime minus 6y prime equals 6x plus 7 e power minus x. Same method here. Y triple prime plus y double prime minus 6y prime equals 0. Lambda cube plus lambda square minus 6 lambda will be 0. So we'll get lambda equals 0 first solution, lambda equals 2 second solution, lambda equals minus 3 third solution, and y homogeneous will be c1 plus c2 e power 2x plus c3 e power minus 3x. As to non-homogeneous part, here with the exponent we have minus x. So we should check if we have lambda equals -1 be the solution of our characteristic equation, but we have none. We have 0, 2 and -3. We don't have -1 here. So yn will be ax plus b by exponent power minus x. Y prime will be exponent minus x, a minus b minus ax. Y double prime will be e power minus x by ax plus b minus 2a, and y triple prime will be e power minus x 3a minus b minus ax. So if you substitute all these functions into our initial equation, we will have 6ax minus 5a plus 6b will be 6x plus 7, so 6a equals 6, 6b minus 5a is 7. From here a is 1, b is 2. So yn will be 2x plus 4 e power minus x, and general solution will be c1 plus c2 e power 2x plus c3 e power minus 3x plus x plus 2 e power minus x.